Nitrogen is one of the most essential and abundant elements in the universe and on Earth. It plays a crucial role in life, industry, and the environment. With the atomic number 7, nitrogen is a non-metal and belongs to group 15 of the periodic table, also known as the nitrogen group or the pnictogens. It is represented by the symbol N and has an atomic mass of approximately 14.01 atomic mass units. In its elemental form, nitrogen is a diatomic molecule, N2, which makes up about 78% of the Earth's atmosphere by volume, making it the most abundant gas in the air we breathe. The discovery of nitrogen is credited to Scottish physician Daniel Rutherford in 1772, although several scientists of that time, including Carl Wilhelm Scheele and Joseph Priestley, had observed it. Rutherford conducted experiments to remove oxygen and carbon dioxide from air and observed a remaining gas that could not support combustion or life. This gas was nitrogen. The name nitrogen comes from the Greek words nitron and genes, meaning niter forming. It was named for its presence in compounds like potassium nitrate, saltpeter, historically known as niter. Nitrogen's atomic structure includes 7 protons and typically 7 neutrons in its most stable isotope. It has 5 electrons in its outer shell, which makes it trivalent in most chemical compounds. Because it needs 3 additional electrons to fill its valence shell, nitrogen commonly forms 3 covalent bonds. This gives it a great deal of versatility in bonding and allows it to be part of a wide range of molecules, from the inert atmospheric N2 molecule to complex organic and biological compounds. Atmospheric nitrogen is remarkably stable due to the strong triple bond between the 2 nitrogen atoms in the N2 molecule. This triple bond requires a large amount of energy to break, which is why nitrogen gas is generally unreactive at standard temperature and pressure. However, this same property makes it useful in creating an inert atmosphere in industrial processes, where oxidation must be prevented, such as during the manufacturing of electronics or in food packaging. To be used by living organisms, atmospheric nitrogen must be fixed, meaning it must be converted into a more chemically available form like ammonia, NH3, nitrate, NO3, or nitrite, NO2. Nitrogen fixation can occur naturally through lightning or through biological processes carried out by certain bacteria, such as those in the genus Rhizobium, which live in the root nodules of leguminous plants. These bacteria convert nitrogen gas into ammonia, which plants can then use to make proteins and nucleic acids. This relationship between nitrogen-fixing bacteria and plants is a key part of the nitrogen cycle, which moves nitrogen through the atmosphere, biosphere, and geosphere. The industrial process that mimics nitrogen fixation is the Haber-Bosch process, developed in the early 20th century. This method synthesizes ammonia from atmospheric nitrogen and hydrogen gas under high temperatures and pressures, using a metal catalyst. The ammonia produced is the basis for nitrogen fertilizers, which have transformed global agriculture by dramatically increasing crop yields. However, excessive use of nitrogen fertilizers can lead to environmental problems such as water pollution, eutrophication, and the emission of nitrous oxide, a potent greenhouse gas. Nitrogen is fundamental to all forms of life. In biological systems, it is a critical component of amino acids, which make up proteins, and of nucleic acids, which form DNA and RNA. These molecules are central to the structure and function of all living cells. Proteins in particular perform countless tasks within organisms, including catalyzing metabolic reactions, replicating DNA, transporting molecules, and providing structural support. Nitrogen is also a part of adenosine triphosphate, ATP, the molecule that stores and transfers energy in cells. In addition to its role in biology and agriculture, nitrogen has many industrial and technological applications. Liquid nitrogen, which is nitrogen in its cryogenic liquid form at -196 degrees Celsius, is used as a coolant in a variety of applications, including cryopreservation of biological samples, superconductors, and even in culinary uses like making ice cream. Because of its low reactivity and inertness, nitrogen gas is used to displace oxygen and moisture in packaging, to protect sensitive materials from oxidation, and in the inflation of aircraft and race car tires to improve pressure stability. Nitrogen compounds also play critical roles in medicine and materials science. Nitrous oxide, N2O, commonly known as laughing gas, is used as an anesthetic and analgesic in dentistry and surgery. Nitrates and nitrites are used in the preservation of meats, though they must be managed carefully due to potential health concerns. In material science, nitrogen is used in the production of semiconductors, stainless steel, and explosives. Compounds like nitric acid and ammonium nitrate are essential in the production of fertilizers and munitions. Despite its inertness in the atmosphere, nitrogen can be part of very reactive and sometimes dangerous compounds. For instance, ammonium nitrate is widely used as a fertilizer, but under certain conditions, it can become highly explosive, as tragically demonstrated in several industrial accidents. Nitrogen's role in the environment is governed by the nitrogen cycle, a complex network of processes including nitrogen fixation, nitrification, assimilation, ammonification, and denitrification. These processes move nitrogen through different forms and compartments of the Earth system. Human activities, especially agriculture and the burning of fossil fuels, have significantly altered the nitrogen cycle, leading to increased nitrogen in the environment, with impacts on biodiversity, air and water quality, and climate. In summary, nitrogen is an element of contrasts. It is both essential and inert, abundant and elusive, simple in structure, yet involved in some of the most complex and vital processes in nature. Whether in the air we breathe, the food we eat, or the technologies we use, nitrogen's presence is fundamental to life and industry alike. Understanding and managing nitrogen more effectively will be key to addressing many of the environmental and agricultural challenges of the future.